Milano Bicocca. Today, Marco Fazzi will be talking about expanding on Cardy-like limit of superconformal model index of 4D n equal 1 A, B, C, D, S. Well, let's say.
Yeah, I actually changed the title of it, so it's this easier one.
I see that now. Okay, yeah. Okay,
I realized it
good.
was,
so everybody gets excellent. Yeah, please go ahead.
Okay. All right, so let me join all the other speakers in thanking the organizers for this nice opportunity. It's actually my second time virtually here in Cortona, and I have to say that my memories from the previous workshop are really nice. So yeah, today I'll be talking about the Cardy-like limit of the n equals 1 superconformal index, and this is based on two papers that I published in collaboration with Antonio Mariti from NFN Milan and Alessia Segati, a pretty solid student of his at the university. However, I do encourage you to have a look at these two other papers that I put here, which were published around a month after we posted ours. Especially the one by David and Zar gives a nice complementary explanation of the main formula that I will be showing you in a second. Let me say from the outset that today I will only be focusing on d equals 4, where d is the field theory dimension. However, a lot of work has been on the same topic, has been done by other people, so not myself, in d equals 3, and some preliminary results also exist in d equals 5 and 6. So this is a brief outline of my talk. First, we're going to see why we care about the black hole entropy and why the superconformal index, I believe, is the right tool to compute the former. Secondly, I'm going to present with our new general formula for the Cardy-like limit of said index. And finally, time permitting, I will show you a few examples of field theories with n equals 1 supersymmetry for which we computed this index. So the problem, as I alluded to in the outline, the main problem we're interested in is counting the microstates for supersymmetric black holes and possibly identify what they are. Of course, this is interesting, or this is a major problem in any theory of quantum gravity, since we believe that microstates are the origin of the Beck-Steenhoek entropy formula, which famously relates the entropy of a black hole, not necessarily supersymmetric, to its area and Newton constant. I'll be setting all the other constants to 1 throughout. So one should ask themselves, first of all, why is this formula true? And secondly, whether we can give it some statistical interpretation, some statistical meaning, namely whether we can identify this entropy as the logarithm of some number, little n, where this number should be the number of microstates of the black hole. Also, let me point out that this formula is an early incarnation of the holographic principle, given that it basically only depends on the area. So somehow it's suggesting us that all microstates of the black hole are concentrated on the boundary namely on its event horizon. So for asymptotically flat black holes, actually we know that string theory gives the right answer. This was shown in a pioneering paper by Strominger and Waffa and many other papers that followed. And essentially these people were able, by counting some states in a given string theory construction, they were able to reconstruct the Beck-Steenhoek formula for the black hole that this string theory construction gives rise to. So a natural question is, of course, whether we can do something similar for not asymptotically flat black holes, but black holes that at infinity look like, for example, ADS, so or anti-de Sitter space, one of the famous solutions of Einstein's field equations. So the natural question is whether string theory can help in this setup as well. These black holes have been constructed by Gutovsky, Real, and other people some 20 years ago, if I'm not mistaken. And in particular, they can be embedded inside a vacuum, so a vacuum solution of string theory, the famous ADS5 process 5. However, they do preserve less supersymmetry with respect to the full vacuum. So they're quote unquote 1/16 BPS, which just means that they preserve 2 out of the 32 supercharges of the full ADS5 process 5 vacuum. Moreover, they have the same conformal boundary as that of ADS, so R across a 3-sphere. And finally, they're characterized by 3 electric charges that we'll call little QA and 2 angular momenta, little JI. And keep in mind that these quantities are actually constrained by supersymmetry. So only 4 of them are truly independent. These are the only features of these black holes that I'll be needing in this talk. Now, the obvious idea here is to use the famous ADS-CFT correspondence by Maldacena, which relates weakly coupled string theory on precisely this background, so ADS5 cross S5, to a four-dimensional field theory, a rather special one, namely N=4 super Yang-Mills based on gauge group SUN. The idea is to use this correspondence here to potentially identify what the black hole microstates are. In fact, if we use ADS-CFT, if we assume that it is true, the CFT side of the correspondence will provide the definition of the microscopical quantum theory together with its degrees of freedom, so that we can identify the black hole microstates to certain states in the CFT at the boundary of this ADS space. Of course, the question is now, what is the ensemble of states in the dual N=4 super Yang-Mills on the conformal boundary of ADS that reconstructs, that gives rise to the Beck-Hocking entropy for the dual black hole. And here, supersymmetry and the charges of the black hole actually suggest what are the states that we should be counting in N=4 super Yang-Mills. And these are the states that preserve the same amount of supersymmetry as the black hole that is embedded in the string theory vacuum, namely 1/16 supersymmetric, so 1/16 BPS states of N=4 super Yang-Mills, which are characterized by spins Ji and charges U1 charges little qi, which would be identified with the two angular momenta and the three electric charges of the black hole under the ADS-CFT correspondence. More generally, again, I'm speaking about a specific ADS5 black hole, which preserves 2 out of 32 supercharges of the full string theory vacuum, and this is dual to a certain set of states in N=4 super Yang-Mills. However, by looking at N=4 super Yang-Mills as a special N=1 SCFT, one may, of course, ask themselves whether this is true for more generic N=1 SCFTs. And if that's the case, we should be counting actually 1/4 supersymmetric, so 1/4 BPS states in a generic N=1 SCFT, or the supercharge that they preserve, I will call script Q. So to summarize what I've said so far, if we have a black hole solution that embeds inside an ADS D+1 dimensional space and has conformal horizon given by R times M of dimension D-1, where M is a certain manifold, then the problem boils down to enumerating 1/4 supersymmetric states in the dual CFT, which lives on this conformal boundary. In particular, when this manifold M is just a sphere, the enumeration is given by the so-called superconformal index of the CFT, which is an object that was introduced many years ago and studied in a series of papers. And even in these early papers, of course, people knew that this may be the right object in field theory to compute or reconstruct dually the black hole entropy. In fact, this result works. So this expectation is borne out. And for ADS5 black holes, we know, due to, of course, a series of calculations, that the entropy is correctly reproduced by the logarithm of the superconformal index of N=4 at large n, where here n is identified with 1/the root of G Newton, and crucially for complex chemical potentials. So before I explain all these words, let me just flash that our expectation that the entropy of the black hole had some sort of statistical interpretation is indeed borne out, given that it's calculated as the log of some number, and this number is the superconformal index of the CFT. So here's the result. I'm just flashing it. The important point to understand here, I think there are two important points in this formula. The first one is the behavior with n at large n. So we see that the black hole entropy actually scales as the square of this parameter n, which on the CFT side is just the rank of the SUN gauge group. And of course, for those who know a little bit about CFTs or N=4, N=1 theories, you may notice that this scaling is exactly the same as the one of the central charge of any N=1 CFT. And these quantities on the right, so if you can see my cursor, these other quantities are precisely the complex chemical potentials that I was speaking about. In particular, these big deltas are associated with the charge operators whose eigenvalues, little QAs, would be the black hole electric charges, and the omega i's are associated with the angular momentum operators, whose eigenvalues will be the little ji's that I introduced before. So the angular momenta of the black hole. And there's a whole complicated story around the chemical potentials that one has to introduce in the superconformal index to obtain on the nose the correct black hole entropy. However, unfortunately, I don't have time to discuss that. Just keep in mind that at the beginning, in the original calculations, people took real chemical potentials and got some sort of mismatch between the gravity expectation and the field theory calculation. However, it was later realized in a series of papers that one has to consider generically complex chemical potentials. So that's the take-home message for this slide. So what is this index that I've been mentioning to? Well, it's just a generalization of the Witten index. If you remember, the Witten index is just a trace of the Hilbert space of the supersymmetric field theory of this operator -1 to the f, where f is the fermion number, it equals 0 for bosons, and it equals 1 for fermions. And of course, you may be thinking, well, in a supersymmetric theory, of course, bosons and fermions are coupled in a sense. So you may expect that there are large cancellations in this trace due to this -1 to the f. And indeed, you would be correct. And it's kind of a miracle, if you want, that by taking complex chemical potentials, so these deltas and omegas, as I said before, these cancellations are quote unquote optimally obstructed, and we can extract a large and a meaningful quantity from this index. So this script Q is the preserved supercharge, as I said before, and these deltas and omegas are the complex chemical potentials. Now, the main point here, rather than focusing on this definition, is the fact that we can actually compute explicitly this index. In fact, the calculation boils down to basically a matrix integral. So it's an integral over the eigenvalues of a certain matrix, basically due to some very powerful result in mathematics known as supersymmetric localization. We can boil down the calculation of this index to that, we can reduce it to the calculation of a finite dimensional integral. So the important point is that we can compute it explicitly, and it's not that hard. And when we take the log of this index, the agreement with the gravity result for the Bekenstein-Hawking entropy of the ADS5 black hole has actually been obtained, as I said before, in 2 limits. So the first limit will be a large n limit that unfortunately I will not have time to discuss here. However, it turns out that the index at large n behaves or is given by the central charge of the CFT. So this n squared that we saw before was actually not a coincidence, and it's there precisely because the index at large n behaves like the central charge of the CFT. The other limit that I will be focusing on in this talk is the so-called Cardy-like limit. Again, I won't have time to discuss why the limit is called Cardy-like, just take it as is. And the limit here basically entails taking the complex chemical potentials, little omega i's associated with the angular momenta to be very small. So you take these omegas to be very small. And then it turns out after some non-trivial calculation that the index in that limit can be expanded in such a way. So you see, again, it depends on the central charges of the CFT. And for those who know, for holographic theories, the central charges will be equal, A and C will be equal to large n. So the second summand actually disappears. And we see that the index actually captures the orders which go like 1 over omega squared and then 1 over omega. And it stops at finite terms. So it does not capture finite terms in omega. Basically, they go like omega to the 0. So I think this is the point where our paper actually improves upon the previous literature that the results were obtaining these 2 papers that I put here at the bottom of the slide. And this is the new formula that we were able to extract for the Cardy-like limit, where under the actually simplification that omega 1 be equal to omega 2. So we identified the 2 angular momenta for the black hole, and this is a simplification. which we would like to, of course, generalize at some point. So let me call that complex technical potential tau. And this is the expansion in tau that we obtained. So as you can see, it's basically of the same flavor as the formula that we had before. It goes like the central charges. It depends, sorry, on the central charges of the dual CFT. However, it also includes terms which go like tau to the 0. And indeed, for example, we see here the appearance, here on the right, we see the appearance of a finite correction, which is constant in tau. Also, let me stress that this formula is valid for any rank n of the gauge group. So we did not take the rank of the gauge group, basically n, to be infinity in this formula. It's valid for generic n equals 1 CFTs, so not just super Yamils, and in fact CFTs which are based on gauge groups of any classical type, so A, B, C, D gauge algebras. And it's valid both for holographic and non-holographic theories. So theories that may or may not have the two central charges A and C equal at large n. The finite log correction, we managed to give it a physical interpretation. And I think we believe that it's given by the minimal charge of any of the matter fields present in the CFT under the center of the gauge group. So the center symmetry, which is usually called Z of G, where G is the gauge group. This formula, we like it particularly because it essentially explains and expands upon previous results. So in two separate papers, finite subleading corrections of this form, so log of something, were obtained for two different sets of theories, namely super-Mills based on any classical group, and toric quivers. It's not important to know what toric means here. The important point is that in those cases, some log corrections were obtained, but the interpretation of this log correction was not clear. And I think now we actually know where it comes from. So let me skip this slide. I just included it for clarity. If you're interested in the derivation of the formula, just ask me in the Q&A session or later on in the breakout room, or you can have a look at the slides that are online. And I think I have like 3-4 minutes, right?
Yeah, thanks. Yeah.
Okay, so let me flash a few examples in the minutes that I have left. So as I said before, the main case that was tackled both from these large n techniques and in the Cardy-like limit was n equals 4 super Mills, based, however, upon gauge group SUN. And in a paper from 2020, again with Antonio and Alessia, we extended it to the other classical groups, so USP, 2N, and SON. And we performed a rather long analysis of this index. Again, you don't have to focus too much on the details here, which I couldn't have time to explain. Basically, you take the index and you expand it in this limit, and it turns out that it's computed by a matrix model. And you have to be very careful about the saddle point approximation of this matrix model. And once the dust settles, it turns out that the index is precisely given by the formula that I showed before, which, for example, in the case of USP super Mills will be given by this thing here. And you can see here precisely that we have this log2 correction, which is consistent with what with our general formula. Yeah, so let me skip this. Finally, we have looked at more complicated examples. So, so far, I would say that most of the literature on this topic is either focuses on super Mills or on toric theories or on so-called holographic quivers, which are based on SU and gauge groups. And we wanted to check whether our formula was correct in other more complicated cases, such as, again, non-toric theories, where toric means in this context that the global symmetry is given by U1 to the cubed. And again, you may think that this is some non-generic condition. However, it does simplify a lot the calculations. Then we looked at theories where the ranks of the SU groups are not all equal. And then we also looked at non-holographic theories. So in the minute that I have left, I'll just show some of these models. For example, we looked at a classic Seiberg dual pair of theories. And we, given Seiberg duality, we expected the index computed in both phases to be equal. So what we did was to compute the index of the phase on the left and the one on the right, or let me stress that, for example, this group here is SU2N. So again, you may think that this is just some mild modification of the theory, the fact that we have SUN, 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 and here SU2N. However, it is not. So you have to be very careful with your calculations. And the fact that, the index matches across the two phases, of course, is an expectation from subreduality, but we were indeed happy that, our general formula basically predicted the form of the index for both phases. So we believe this is a non-trivial check of the validity of our formula. We also looked at some more complicated theories, which again, I will just flash here. The details are not that important. The formula is valid in this case as well. This would be, for example, models which are non-toric. And finally, just for the sake of checking, improving generality of our formula, we also looked at non-holographic n=1 theories, such as SQCD, and also some examples of n=2 theories. And let me focus just on one model. So we took this model that was constructed, I think, in the 90s. This is an n=2 conformal field theory based on gauge group SUN, and the matter content is given by one symmetric hyper and one antisymmetric hyper. It allows, it can be engineered in string theory, but that's not too important. What is nice is that we computed the log of the superconformal index for this model in the Cardy-like limit, and it nicely matches with the expectation from gravity, which was obtained recently by Hosseini and Zaffaroni. So what they did was basically to generalize the calculations for the Beck-Sinokian entropy, which are valid in the case of 1/16 BPS black holes. They generalized it to cases with more supersymmetry, which will be dual to, for example, n=2 SCFTs. And we found that the Cardy-like limit of our index nicely matches with their expectation for the Beck-Sinokian entropy, again, lending more credibility to our formula. So let me conclude. We provided, I hope I convinced you, we provided a formula for the Cardy-like limit of the superconformal index of generic n=1 SCFTs, which are based on any classical gauge group. And this formula extends previous results, which were valid at lowest order in tau, or they were valid for non-generic theories, such as Supernia-Mills or toric quivers. The formula includes some leading and subleading contributions in 1/tau, as the previous formulas did. However, it also includes a finite log corrections, and we gave this finite log correction an interpretation in field theory as the minimal charge of the matter fields under the center of the gauge group. Let me just stress, that actually we do not have a rigorous proof of this formula. We can explicitly determine leading and subleading contributions by looking at the matrix model interpretation of the index and by using an ansatz for this dominant saddle point. But we do not have a proof, for example, of the appearance of the finite log correction. We just know that in all examples that we checked, the log correction is there, and our interpretation explains why it is the number that it is. As an outlook, I have put on some points. You can have a look at them or ask me in the Q&A.
Yeah.
I think the most important one is would be giving an ADS-CFT interpretation to the finite log correction. So finding the holographic dual of these log corrections would be very nice, because it will basically give a quantum gravity, quote unquote, correction to the entropy of asymptotically ADS black holes. And I think I'll stop here. The other points, you can have a look at the slides.
Thanks very much, Marco. Thank you. And Francisco?
Thanks, Marco. I appreciate very much your talk. I have a general question, which actually you partially addressed at the end. So you're saying that you don't have a general proof, so you match basically these results. It's like a consistency checks in certain elements, and that's nice. That's often done in this business, so I kind of appreciate that. But the question, on the other hand, also arises when you can test it, you can test it with explicit computation in gravity, in quantum, I guess, in supergravity. But the point is, how can you go beyond than the supergravity? I mean, if you cannot test them, when can you believe them? So let me, maybe I was a bit, what I said was a little bit confusing. Let me clarify 2 points. So first of all, the leading and subleading terms, which go like, say, 1/tau squared and 1/tau, we can derive them
concretely. So in that sense, you know, with the rigor of physics, we can definitely show that the formula is correct. What we are not able to extract directly from the, if you want, the matrix model representation of the index is the finite log correction, or rather, we do not know whether this formula would hold for any n equals 1 CFT. We believe it does because we checked it in so many non-trivial examples across dualities. We check other things that I didn't have time to mention here. So we strongly believe that it's correct. Regarding your second point, I think you were asking, whenever you lack the gravity dual, how can you check whether what you're saying is correct? So let me stress, however, on that point that the gravity dual is semi-classical, is weakly coupled. So it will not include the finite term correction, for example. So even if you had the Becken-Synokyan entropy directly computed from gravity, the typical calculation would not include the finite log corrections. So in any case, you wouldn't be able to check across, you know, from gravity.
So you're saying we don't even know whether that's correct?
Well, it's not that, I don't think it's like we don't know, it's rather ADS-CFT is really hard when you include subleading corrections. So you would really, you would have to do these hard derivative corrections to ADS-CFT, which is in sometimes cases done, as I put here, you know, see, I put here.
Yes, so very quickly, and then I will not go further. So the question is that, so in supersymmetry, many things collapse by supersymmetry, many things get actually. So you use the superconformal index, but that might be not the only way to do that, or it might be actually another way to do it. If you could envision another way to get that, which does not involve the superconformal index, what would that be?
You mean to compute the entropy?
Yes.
I think it's the right tool actually for the job. So a partial answer to your question would be, suppose I say that ADS-CFT tells you that, you know, this specific CFT is dual to this specific weakly coupled vacuum of string theory. And then I also tell you that the black hole that you can embed in the ADS vacuum of string theory has a certain entropy as computed by the Becken-Synokyan entropy formula, sorry. Then you believe that ADS-CFT is true. So you say, well, okay, there must be a set of state in the CFT which accounts for this specific entropy. And given you know that the black hole preserves, say, 1/4 BPS, so only one supercharge in the generic n equals 1 case, then you know basically that what you have to count is all 1/4 BPS states in the CFT. And that would be like computing a grand canonical partition function. However, that's super hard. We do not know how to do that. What we know how to do is to calculate the superconformal index. And as I said it at a certain point in the slides, I don't remember when, it's kind of a miracle that it works because of the constellations. So the trick was to allow the chemical potentials to be complex. And then we found that indeed the expectation was borne out. So regarding the question, do you know another quantity to compute to reconstruct the same entropy? I would say if we knew how to do it, the right tool for the job would be computing all quarter BPS states. So the quote unquote grand canonical partition function.
Okay.
Thank you.
Thanks.
We have a last question by Andrea. And we don't have time for more, actually. Thank you, Andrea.
Yes, at a certain point there was an entropy which was imaginary.
Yeah.
Can you comment?
Yes, yes. I actually wrote real. Yeah, I can comment on that. Let me. Good observation here, right? Because of this I.
Yeah.
However, keep in mind that these are complex chemical potentials. And also that, you know, and I put here a star, or the star means Legendre transform of log of the index. So what happens is that actually you have an extremization problem where you have this formula here, say plus a constraint times the Lagrange multiplier. Once you extremize this right side, the right-hand side of the equation, and you plug back in the values in this formula, when you plug the values at the extremum of the extremization problem for the complex chemical potentials, it turns out that this entropy is real, as you expect.
So this is not actually the entropy.
Yeah, it is the entropy. I should have put here, so beside these deltas and omegas, I should have put a little star, meaning at the extremum value for the extremization problem. So complex times I can be real, right?
Ah, okay. So these numbers are not real.
No, complex chemical potentials. In fact, it's crucial that they be complex. Otherwise, you don't get on the nose the equality with the expected gravity result.
You are saying that the entropy should be imaginary when the chemical potential is imaginary? I don't think so.
I'm saying that this is the formula for example. So let me put it this way: if you compute the log of the superconformal index, you will get this. Okay. Now you go back to the gravity calculation, and then there is a formula that I've not written here, which tells you that the entropy, has a certain shape, functional shape, and then there is a plus lambda times in brackets a certain constraint. And the prescription tells you that you have to extremize this whole functional. And once you find the extremum values, so you basically compute derivatives of this whole functional with respect to the deltas and the omegas, once you plug back in the extremum values of these complex chemical potentials, on the one hand, if you want, you can reconstruct the Becken-Sinokin formula that I think I have in the slides. It's the typical square root of the various electric charges.
Okay.
And on the other hand, you get equality with the index.
Fabio, can I make a little comment about that? Because maybe this helps. In general, in a theory that is CP invariant, if you do the Legendre transform by minimization, the chemical potential is always imaginary. So this is a thing of thermodynamics. It has nothing to do, I mean, it is more general. Marco is absolutely right, because it is an absolutely general thing for any CP invariant theory, full stop. You always have imaginary chemical potentials.
I agree with this statement.
Okay, very good. So that's a good point where to stop. So we thank Marco again and actually all the speakers so far.